Hello everybody, welcome back to another video teaching 1D kinematics. In this video, I will be covering a more in-depth detail graphs of these kinematics equations. So we will have 3 graphs for each questions. We have 3 questions here. And the goal is to form the other 2 graphs that aren't given from the 1 graph that is given. So let's start by overviewing some basic equations. So we know that for this first problem, I'll go down here, V equals d over t. That's just velocity is equal to displacement over time. So given this equation, we can solve for d and just multiply both sides by t. And we get Vt equals d. Now, let's observe the V versus t graph. Actually, I'll bring an imaginary example down here. Oh, very bad line right there. So let's say that our velocity is just this constant. Wow, I'm bad at drawing today. This constant v, 1, and then let's say, I'll call this v naught. And then let's say this is the velocity, and then this is the time axis. So let's say we start at 0 times 0, and we go to time t naught. Now, if we look at our equation, v times t, so this side of this imaginary rectangle times this side of this imaginary rectangle, we could see that distance is equal to the area under a velocity versus time graph. So let's get started with the first question, where we are given our initial displacement is 0, by the way. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 of this constant velocity, 18 seconds is constant velocity. And then we have 1, 2 seconds of this velocity that is decreasing. We will cover that part in a bit, but first off, let's go to our acceleration versus time. And let's cover this concept. So let's say we have a v versus t graph, and let's say we have a constant slope, which is m, which represents slope, equals y minus, or y2 minus y1 over x2 minus x1, which is equal to delta y over delta x. Now, we also have the equation that A equals Vf minus Vi over delta t, which is equal to delta V over delta t. Now, are you picking up what I'm putting down yet? Our slope of a velocity versus time graph is equal to acceleration of that function, or of that particular particle. So, as we can see, for the first 18 seconds of this particle's motion, the slope, delta v over delta t, is equal to 0 meters per second squared, since there is no change in acceleration. Or since there's no change in velocity, there must be 0 acceleration. So we will draw a straight line from time 0 to time 18. Now, let's look at this last little segment right here. This segment, as you can see, v, we have a slope of our rise, or our delta v, is equal to 1 meter per second, and our delta t, the time it takes, is equal to 2 meters per second. So delta v over delta t equals, oh wait, this is supposed to be, it's just seconds, sorry about that. Second, delta v over delta t equals 1 meter per second divided by 2 seconds, which is a equals 1/2 meter per second squared. So we can draw in an instantaneous jump to the 1/2 line. Oh, I'm on the square setting. And we will have a straight line. That is a horrible straight line. A straight line at the point 1/2. And that looks like it's decreasing. Bear with me. There we go. So this is our completed acceleration versus time graph, and that is correct. So in order to determine acceleration from a v versus t graph is slope of v versus t. And then since we know that distance is equal to this area, we can start doing this following question, where for the first 18 seconds we have a box of length of base 18 and of height 1 seconds meter per second. So we know area of a rectangle, base times height, area equals 18 seconds times 1 meter per second. A equals 18 meters. So we start at 0 meters and we go up to 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 meters at the 18-second mark. And this will be a straight line since every square is equal in distance. So it is just constantly treading and increasing. This is our velocity, which I do not need here, so I can get rid of this. So here to here. And now let's look at this last little bit. So when we have an acceleration, the magnitude of the acceleration is greater than 0. So the acceleration just isn't 0. We know that our d versus t graph is going to be curved. And if the acceleration is positive, wait a minute. Sorry about that. I do not have a negative value here. I just realized this. This is supposed to be going down here, but I did not have a negative axis, so I accidentally took the absolute value. So since our acceleration is negative, we know that our graph is going to be concave down. So it is going to look like this because, as you can see, the velocity here is greater and the velocity here is less because A is dragging velocity down. So we can just use the area for a triangle for this part. So we have A equals A, capital A for area, equals 1/2 base times height, and we have 1/2 2 times 1, and you get, these cancel 1. So we move up 1 more meter in these 2 seconds, and then our graph will look like this. So that is our first question complete. Now, it should be much easier from here. Hopefully, no more mistakes with the negatives. I won't do it again. Whoa. All right, so for our second problem, you could see we have a straight line of constant slope, which is just what a straight line means, of our diversity graph. So since we have this equation, v equals delta d over delta t, which is also equal to the slope of this line, we know that velocity is the slope of a d versus t graph. So we can just observe 2 points here. Let's look at 0, 0, and then 1, 3. So m equals y2 minus y1 over x2 minus x1 equals v2 minus v1 over t2 minus t1. And then that is equal to 3 minus 0 meters per second. No, just meters. Over, sorry, I thought I was looking at the different graph again. Over 1 second minus 0 seconds, which is equal to 3 meters per second. So for this entire interval, we have a constant line of this constant slope 3 meters per second. It's heading through here. So that is our velocity versus time. And then given that acceleration is our slope of our diversity graph, and this slope of the velocity versus time graph is equals 0, we can determine that the entire acceleration for this entire particle's motion throughout the given interval, or actually forever due to this arrow, is just 0, which was a very speedy second problem, which may not be the case for this last one, but it probably will. It will probably be very fast also. So we are given the acceleration for this graph, and we need to find velocity and distance. So we have a equals delta v over delta t. Delta v equals a times delta t. And then what would you know it? This represents delta t. And then this represents a. So our change in velocity is equal to the area under the curve of an A versus T graph. So we just have an acceleration of 1 meter per second squared times a change in time of 3 seconds, which is equal to our velocity, change in velocity, which is VF minus VI, and I gave you that VI is 0 over here, so VF minus 0, so that term goes away. So we have 3 meters per second is our final velocity. And then since this is constant and each individual mini square that we split up has the same change in velocity, given that it's the same time interval, we know that our change in velocity for this is going to be constant and linear, and it is going to follow this line. And then once our acceleration has reached 0, that means that no more area is being added under this curve, so our velocity is constant. So that would mean that the slope of this graph must be constant as well. So we can draw a straight line for the rest of this interval. And that is our v versus t graph. Now for this d versus t graph, we are not going to have enough space. So after a certain point, I will just end up drawing an arrow. So first off, we know d equals area of v of t graph. So for this first little bit, we know that the area, I'll just draw on the graph, equals 1/2 base times height, which is equal to 1/2 3 times 3, so 9/2 area, which is equal to our distance traveled during the first 1, 2, 3 seconds. So 9/2, that's just 4.5. 1, 2, 3, 4, and then a little bit over for our first 3 seconds. And since our acceleration is positive, we know that this graph must be concave up. So it starts slow and then it gets faster over time. Oh, that was a very bad line. So that is our graph that we are given. Here, I'll make it more realistic. Shoot. Quite difficult to draw this. There we go, that's good. Now, since we know that the slope of a distance versus time graph is equal to our velocity, and our velocity is 3 for the rest of this time, we know that our graph must have a slope of 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Oops, did not mean to draw this one. Never works. There we go. And 1, 2, 3, and then that is the rest of our graph. Let's go in with our straight line. And then that is our distance versus time graph for this problem. And now this is just a straight line for the rest of the problem, but it does not fit there because this is a lot of area. So that is our final answer. Sorry for all the mistakes with the units and stuff in this video. I was very sidetracked and thinking that I was working on a different problem when I wasn't. It's hard to see what you're doing while you're like making all these problems up in your head and just thinking about them. So I hope you all enjoyed. Hope you learned a lot. I hope this video helped you a lot. Let me know if you have any concerns in the comments, any videos you think I should make if you need more help on certain parts of this. I might make a part 2 to this video. I think this is an extremely important fundamental idea for understanding kinematics. And I think that will do it for this video. Have a great rest of your day. Like, subscribe, do all that, please. If you watched this far, you're probably subscribed already. But yeah, help me out a lot if you could do that. Thank you and have a great rest of your day.